talk about density. What if you had equal volumes of fresh water and salty water? Which one would weigh more? Well, it's fairly intuitive that the salty water would weigh more because the salt adds weight to the water. In fact, if you took a liter of water from the ocean and evaporated all the water away, you'd end up with about 25 grams of salt. Now what about warm water and cold water? Which one of those weighs more? Well, if there were equal volumes, the cold water would weigh slightly more. And so we expect the bottom of the ocean to be filled with cold, salty water because it sinks to the bottom. The surface of the ocean should be warm and fresh, and that's exactly what we find. The surface waters are warmed by the sun, so they're hotter than the deep waters, and also we have freshwater input from the land around the oceans. Now the density gradient between the warm fresh water at the surface and the cold salty water at depth is called the picnic line. And the picnic line turns out to be very important in determining a lot of physical and biological properties in the ocean. So here we have a tank full of fluid, and what I'm going to do is take this barrier and put it in here toward the end of the tank. Slide it down. Now what I'm going to do is mix the water in the tank and add some food coloring. This is just ordinary store-bought food coloring. We'll use green to look like a chlorophyll maximum. Now I'll stir it up. The question is, what's going to happen when I remove the barrier? Most people would guess that it's either going to completely mix, it'll go to the top, or it'll go to the bottom. So let's find out. It's pretty amazing. And the things to notice are that it's moving very slowly and that the amplitude, the vertical extent of it, is pretty big compared to something that you might see at the surface of the ocean. So this is an internal wave in the ocean, and it will oscillate back and forth a few times before it loses enough energy that it dies out. And this is a lot like the interior of the ocean. The movements in the interior of the ocean are very slow, but they're also very large vertically. So waves inside the ocean might only move at 25 centimeters a second, but they can be 100 meters tall. If you saw a 100-meter wave on the surface of the ocean, you'd get very worried. So the question is, why did this happen? And the way I had originally set the tank up, we had a layer here at the surface that was fresh water, and a layer of salty water down below it. The salty water is more dense and it would tend to sink, so it stayed on the bottom of the tank. And this is just like the ocean. The surface waters of the ocean tend to be warm and fresh, and they float. The deeper waters of the ocean are cold and salty, so they sink. And the region that separates the warm fresh water from the cold salty water is called the picnic line. It's a region of strong vertical density gradient in the ocean. Alright, so what happened in that demonstration? Why did the water do such an unusual thing? Well, let's look at what the density looked like in the tank before I put the barrier in, and then what happened after we put the barrier in and mixed. So if we look at the tank, let's draw a graph here where this is the top of the tank and the bottom of the tank. And this is going to be the water density. Where we have low density over here and high density water over here. This would be the cold, salty, and warm, fresh. So at the surface of the tank, we had low density water, and that went about halfway down the tank. And then the density suddenly increased where we had the salty water below. So that was what a density profile looked like in the tank. Now after we mixed the salty water with the fresh water, and we ended up making water that was intermediate in density. So it was saltier than the fresh water, but fresher than the salty water. When I pulled the barrier away, the only place that water could go was below the fresh water because it was too salty for that water, and above the salty water because it was too fresh for that water. And so we ended up with a density profile that looked like this, where we made a third layer right here, which is water that was intermediate in density between the surface and the bottom. And the only place that water could go was to split the top and the bottom layers. So one of the really striking things that you saw in this demonstration is that plug of green water moved so slowly across the tank, and also its vertical motions were very large compared to anything you'd see at the surface of the tank. And this is characteristic of the ocean. And if we look at our tank from the side, a wave inside the tank will be very large amplitude and very slow. So it might look something like this, and move very slowly to one side and then the other. At the surface of the tank, a wave will be much smaller, and it'll move much more quickly. And this is because of the restoring force. The restoring force inside the ocean is caused by the density gradient. So we have warm, fresh water overlying cold, salty water, and that density difference is actually very small. And so these waves can move up and down over very large distances, but they move very slowly. It's the difference between jumping up and down on planet Earth and jumping up and down on the moon, where you'll go much higher, but it'll take much longer to come back down. At the surface of the ocean, the density difference is between the water and the air. And this is a very big density difference, and it makes the waves very small, and they also travel very quickly. And so what we see inside the ocean are these very large amplitude waves. A wave inside the ocean, it wouldn't be unusual to find one that was 30, 40, 50 meters in amplitude. And if you ever saw that at the surface of the ocean, you'd be very worried. This is bigger than most of the buildings that we can see. And so surface waves tend to be just a few meters in amplitude. They move quickly. Inside the ocean, the motions are very big vertically, but very slow. And the picnic line turns out to be a very strong control on the biology of the ocean. And we're going to explore that now. So when the wind blows on the ocean, it can cause turbulence and make mixing. Now if you're a phytoplankton in the ocean, a little plant in the ocean, your job is to get enough light, which is up here at the surface, and to get enough nutrients. And unfortunately, all your friends have taken away all the nutrients, so most of the nutrients are down here in the lower layer of the ocean. So how do we get nutrients from the lower layer through the picnic line and up into the upper layer? Well, a lot of that is done through mixing caused by winds. So let's see how effective wind mixing might be in this situation. So I'm going to make a vertical streak of dye, and we'll see if we can mix it just by blowing on the top of the tank. Alright, let's make a really big hurricane. So you can see the dye at the surface has been mixed away. The dye at depth is still sitting there, and it's not mixed up through the picnic line. It takes a surprising amount of energy to mix the water, the heavy water, up to the surface and to push the light water down. And that's what the wind is trying to do in the ocean. But because the sun keeps putting heat in and warming the top of the ocean up, it makes it hard for the wind to do that mixing. And so this is the problem that the phytoplankton face. The light's at the surface, the nutrients are at depth, and they rely on the wind and other forces to get the nutrients up to the surface waters. So what have we learned from this little demonstration? Well, first we've learned that the interior of the ocean is layered or stratified. The light water lies on top and the cold, dense water lies down below. Second, we've learned that waves inside the ocean are big and slow. They move 10 times slower than waves at the surface of the ocean, and their amplitudes can be 10 times as big. We also learned that the picnic line is a barrier to mixing. The picnic line is a region of strong vertical density gradient, and it takes a lot of energy to move the dense water up and push the light water down. And so it makes it much harder for wind mixing from the surface to penetrate all the way through the ocean. Finally, we also learned that it's really difficult to move nutrients upward through the picnic line. It takes a lot of wind energy to move the nutrients from the deep nutrient pool below the picnic line, through the picnic line, up into the sunlit waters where the phytoplankton can take advantage of them. And so the density layering of the ocean, the stratification of the ocean, turns out to be a very strong control on the physical and biological dynamics of the world's oceans.